Hi, welcome back. And in this video, we want to look at something called effective digital levels. And I think we are building, remember the large picture of what we are trying to do? We are trying to build up to what a signal conditioning circuit should do. What is the function of a signal conditioning circuit in a medical instrumentation system? Okay. So, we were looking at the analog to digital converter in the previous videos, and we said the analog to digital converter converts an analog input into a digital output, and this needs two steps, right? One of the steps is sampling, which is basically discretizing the time axis, and the other step is quantization, which is discretizing the amplitude axis. Okay, so to further think through these ideas, let's think about the analog to digital converter of this analog signal that we looked at last time. And let's ask the question, how many digital levels does this signal span, right? So how many digital levels does this signal span? So if you look at the levels, it actually spans all the 8 levels of your ADC, right? Now, that is a good thing because what we are then saying is the analog signal is basically using all of the digital levels to be represented. Okay. Now take a look at this signal in the next slide here. So this signal is basically the same signal as before, but it has just been shifted down. Now if I ask the question, how many digital levels does this signal span? How many is that? The answer is 1, 2, 3, 4. So even though the ADC has 8 levels, the signal is only spanning 4 of these levels. Now, is that a good thing or a bad thing? The answer is it's a bad thing. Why? Because in this case, we were dividing the 0 to 5. If this analog signal was between 0 to 5 volts, we were dividing the 0 to 5 volts into 8 different levels, right? But because the signal is shifted down, these 4 levels are not being used at all, and all these signals that are below 0 volts are just going to be mapped on to the bottom level, which is 000. Okay, and effectively we are only going to have 4 digital levels, which is a 2-bit conversion, even though our ADC can do a 3-bit conversion. But because this signal is not aligned properly with the input range of the ADC, you get only a 2-bit conversion and therefore more errors. Let's just look at that a little bit more. So if I sample this signal, what do I get? I get my samples like this, right? And if I quantize it, what do I get? Quantize it, I would get a signal like this. So these 2 points are also going to be just mapped to 000, right? So basically I have almost, it's like I have cut off the negative part of the signals. So this is not something what we want. Let's take another example. So let's take an example of this signal. So this is the same analog signal that we have been looking at all along, but it's a much more compressed signal. Now, and let's ask the same question. How many digital levels does this signal span? Now, this signal only spans 2 digital levels. Now 2 to the power 1 is 2. So basically what we are doing is we are just doing a 1-bit ADC, analog to digital conversion. Only a 1-bit analog to digital conversion. Even though we have 8 levels available, we are only using 2 right now. Let's try doing the sampling and the quantization for this particular signal. So if we sample, we get some signals samples like that, and if we quantize, you get a signal like that. And you can see that this is not looking much like the signal that we have at all, right? And so uh, what's happening is that if your input to the ADC is not matched up with the ADC range properly, you start getting distortions in your signal, and you get more errors than what uh, you than what is actually necessary, right? You can do the ADC conversion with much less error, but you are getting much more error here. So what do you do then? So let me just try to. So the question is, what do we do here? And the answer, and we'll look at the answer in the next video.